Alright, so I should be simulcasting to both YouTube and Discord at the same time now. I think I can see both streams going, so I'm gonna close my YouTube tab. There we go. Alright, thank you. Thank you for the confirmation. And then let me place my Discord closer to the left-hand side. There we go. Alright, so what you're seeing on the screen right now is kind of a reminder for myself, of what I need to talk about today. And I surely hope everybody has a chance to kind of look into the process of how a single instruction executes within the processor, at least replicate the experiments or the process that I did in class last week, especially with one of the instructions that I did not even talk about, because that would be good exercise. That's going to be good exercise for you guys to understand a little more about how the processor works. So from here on, I know this is before the class starts, but since a few people are on already, I might as well just kind of start yakking a little early. Right. So the key is, at this point in time, the processor really is self-documenting along with the content of the ROM. Um, I'm hoping everybody will be able to figure out, how instructions execute, what each opcode actually does, and the only thing that is slightly mysterious is, how the assembler works. Okay, and that I would call that slightly mysterious because even the assembler is open sourced. It is just a gigantic spreadsheet with some custom Google script that to support certain things that normally is not really good to do inside the spreadsheet. So I had to write some of the Google script functions to make it more complete. So other than that, this entire thing really is open sourced. I mean, even Logisim is open sourced. It is written entirely in Java, and the jar file that you got actually includes all the source code. If you just change the extension to zip, and then just double click on it, you can actually unzip the whole thing and get to read all the source code of Logisim. So that's how I like to teach this class. Is for those of you who were self-motivated and curious, you can drill as deep as you want. There's no hard pan. There's no rock underneath. If you keep shoveling, you can go deeper and deeper until you get to the layer where I really don't know how Google implements Google script. Yeah, that part I cannot explain either. So there's that. We got about a minute to go, and I can answer questions if there are any, in the text channel. Or if you want to use a voice, I think that's fine too. I enabled your voices too. All right. Yeah, so we're gonna have a fun class today. This lecture is going to be quite fun because we're going to talk about branching. We're going to talk about how to trace the execution of your code, which is pretty much the only way you can decode your program. I mean, debug. Sorry, you can debug your program is to look at the trace. When your program executes. So knowing how to do that and how to do it effectively is really quite important down the road. From here on, we'll be writing code. We're gonna transition gradually from looking into how a single instruction executes to trying to put together programs using multiple opcode to collectively do a particular thing, and then we'll talk about how to compile C code into assembly code. Yes, I use C instead of C++ because I don't think object-oriented programming really needs to get into this class, so I'm only focusing on the procedural part of C++, which most people just call, okay, that's just plain C. All right, so let's go ahead and get started. I'm just gonna adjust a little bit of my mic here because I need to listen to myself a little bit more. It's really weird. If you are recording and you cannot hear your own voice, that's just a really weird feeling that I cannot quite get accustomed to, despite having taught online for as long as I have done so far. So that's just kind of interesting. Anyway, let's get started. Okay, so today we're going to talk about the Jmpi instruction, which is the unconditional branch instruction. And we're also going to talk about how we compare the values in registers and also how we perform conditional branches. These are the only mechanisms by which we can implement control structures. So we don't have if then else, we don't have for loops, we don't have while loops, we don't have do loops. All we have are branching. Okay, the JMP and the JXI instructions, and also labels. I mean, labels are really just for designating where we want to go in one of these instructions. And then we'll talk about how to trace the execution of code. And this portion is not populated because this is for the most part a reminder to myself of what I need to talk about. So we'll talk about the simple but painfully tedious in terms of how to analyze the result. Okay, so let me to analyze. Okay, because it's easy to perform, but when you get to look at the output, you go like, oh, do I really have to kind of visually go through all of this stuff here? The second way is a little bit more painful. It's a multi-step thing, but when you get to the trace, you go like, wow, this is really clean. I can actually read this trace, in a much more convenient way compared to the previous one. And then there's the last way, which is my way. It is called the since I use Linux way. And since Linux is open source, don't let it prevent you from using this method too. It's just that you have to somehow install Linux on your system. If you use Windows, the best way to do it is WSL2. I mean, that's like really easy to do, but you do need to learn a few, commands in Linux, using the command line interface. That's something you're gonna have to do anyway. Once you move on to a 4-year university, there's a pretty good chance that you're going to be using Linux once you move on. So let's get started. So the way we're going to get started here is to go with the opcode table, and we're going to look into the Jmpi instruction, which is this one here. And I'm going to zoom in just so that we can see better what it is saying. So the Jmpi instruction has a constant opcode. The opcode is just 40 in hexadecimal, and this is the mnemonic, and it has an immediate operand, which is what the I here. This is oops. Okay, I just clicked the wrong key on my keyboard. So this I means we have an immediate operand, which basically means okay, that can be any expression that evaluates to a particular value, but it has to be resolved at assemble time. It cannot be a runtime kind of value. And the description of what it does inside the processor is very simple. Originally, I was thinking, oh, it's deceptively simple. No, it is just simple. It is just using whatever the program counter is pointing to update the program counter itself. That's it. That's all what Jmpi is going to do. So why don't we start with this particular instruction, and we're gonna hack some code, and then we'll demonstrate how it works. All right, so I'm not seeing any questions in the text channel, which means I am going to get Logisim started, and then we'll go ahead and do something. All right, this is actually for my other class. Let me get out of this, and we'll go ahead and start Logisim. And when you start Logisim, you're going to be starting the processor circuit file now. So it's inside my processor subfolder, processor 0004.circ. There we go. And here we have the processor. All right, so I'm going to hand assemble the instructions that we're going to trace today, and I'm going to put it into Joplin, okay, just so that you can see how the whole thing can be hand assembled instead of needing the assembler to do everything. All right, so I'm gonna put it right here. Okay. All right, so we're gonna write some code, and this is how you use Markdown to indicate whatever is between the two lines of three backticks is going to be code. And since this assembly language is not recognized by Markdown, I'll just not specify the actual syntax here, because otherwise you can always write down C, JavaScript, or whatever language you're using. It recognizes a good list of programming languages, including Python, but this is not one of the well-known languages. So we'll just go ahead and type our code here. So we're going to just do a Jmpi to location 5, okay, and then at location 5, we're going to have the halt instruction. So now the question is, how do we make sure that we have enough spacing between the Jmpi instruction and the halt instruction? Because whatever I fill in here needs to take up 3 bytes. Okay, so we need to take up 3 bytes over here. There's no quick and easy way to do it. I wish I implemented that feature into the assembler, but there's no way to skip forward. The Jmpi instruction itself is going to take up 2 bytes because there's one opcode to specify Jmpi itself, and then there's 1 byte for the immediate value itself. So it takes up 2 bytes. So it takes up location 0 and 1. And we want the halt instruction to be at location 5, so we need 3 more bytes here. Now there are many ways to fill these 3 bytes up. You can just say no up, no up, no up, no up. That would be the easiest way to fill up these 3 bytes, because each no up instruction takes up, guess what, 1 byte. You can also use just the byte directive. Okay, I will change one of them to the byte directive. It's just a byte. It doesn't even matter what the value is, because we are not going to read this particular value here. So there are many ways to do this, but the point is we want the Jmpi instruction to start at location 0, and we want this halt instruction to be at location 5. Well, this is how you look at it from the perspective of just writing the code. But if you are in the simulator, it is far easier to do it over there. Okay, so let me go to the simulator, zoom in, because it's actually zoomed quite a bit out already. So typically I wanted to zoom into just a little bit more than 100%, for presentation purposes. So what I need to do is to put a 40 here. That's the opcode. Okay, that's something that we just looked up from the opcode table. And then the next byte is the immediate value for the Jmpi instruction. And I already said we want to get to location 05. So we put 05 over here. And then we get to location 05, which is this byte over here, because this byte is location 04 as the address indicates. So this byte over here would be location 05, and we'll just put a halt instruction here, which I just typed 01 on the keyboard, and it appears as 01 in that byte. So this is how I just kind of specify the program, just by changing the RAM location without using the assembler at all. Now, if you are to take this code here, okay, let me change this back to no up. If you are to assemble this program, you will see that it will give you exactly the same content in RAM. Okay, it's just that I can hand assemble a fairly simple program like this without using the assembler. So let's go ahead and track this down, okay, because the next thing I wrote down on my list of things to do is to edge by edge trace this entire program. Now we are going to transition from edge to edge tracing out to tracing by instructions. Each step is the execution of one instruction, because if I do this edge by edge tracing the whole time, we are not going to be able to cover all the material that we need to go over in this class, because ultimately we want to be able to implement recursive functions in C using this processor, right? So if we are just doing edge by edge tracing the entire time, we won't have enough time to do that. Alright, so the next step is to do the edge by edge tracing of the Jmpi instruction, and we're going to focus on this particular mechanism here, because this is the microcode mechanism, and each microcode location, which is basically each location in ROM, is outputting something through the D port in order to tell all the other components, including the registers, the multiplexers, the demultiplexers, RAM, and the decoders and whatnot, and also all the stuff that can do calculations, the adder, the subtractor, the bit shifter, and so on. So this output here, okay, let me highlight which one I'm talking about. This D port, the output of the ROM, is actually going to dictate how the rest of the processor is going to function. So that's why we start here. Okay, we are at location 000 because the microcode pointer is at location 000. And so this is what the processor is configured at this point. Now we have talked about this many times already. This is the fetch cycle, and all we're going to do, I'm just going to do a rising edge. So what we're going to do is to load whatever the program counter is pointing to into the instruction register. So if I have a Control T on the keyboard, you can see how the instruction register is now updated to 40. The falling edge is going to update the microcode pointer itself to 001. Not a big deal. And then the next rising edge is going to auto increment the program counter. Now this is really important, because if I say the program counter gets whatever it's pointing to, it seems kind of awkward, but it's not, because we have already incremented the program counter at this point. So Control T, you can see how the program counter is auto incremented to 01. And then this falling edge is also going to be very important. This is the decode cycle, which basically takes the content of the instruction register, left shifted 4 times, and then put that result into the microcode pointer. Because the instruction register right now is 40 in hexadecimal, when it is left shifted 4 times, it becomes 400 in hexadecimal. We only got one extra 0 because each hexadecimal 0 has 4 binary zeros in it. Okay, so that part is kind of important. So here comes the falling edge, Control T, and we can see how we are now at location 400. So this is where things get a little bit interesting. Okay, so for anyone who is thinking, I have no idea what just happened, you probably want to review the video and the notes that you probably should have taken in the lectures from the previous week. Okay, so last Tuesday and last Thursday was when we talked about these execution cycles, how we get to a location of ROM that is specific to the opcode that we are interested in. So review, take notes, and if you have any questions after that, I'll be more than happy to answer those questions. And from the lack of questions in the text channel, I'm going to assume everybody is cool with this. Yeah, I know it's a very bold assumption, but I'm going to make it. So anyway, now that we are at location 400, we want to find out what is going on here, right? Now, based on the opcode table, which is here, we kind of know what is supposed to happen, right? Because we know we are using the program counter to point to a location in RAM, and then retrieve the value of that location, and then use it to update the program counter itself. So we kind of know what components should be active and the pathways, how the intended pathway. We just may not know exactly how the pathways are formed. And then Matt said, I'm having a tough time visualizing the left shift turning 40 to 400. Alright, so that has to do with the merger. This merger here, which is also called a splitter if it's the other way around, this 0 is contributing to bit 0 to 3 of whatever is going into this multiplexer, and then this tunnel, which is basically just the output of the instruction register, is contributing bit 4 to bit 11. That's effectively a left shift by 4 bits, because we are filling in bit 0 to bit 3 with all zeros and then moving everything. So the original bit 0 from here becomes bit 4 over here. The original bit 1 over here is becoming bit 5 over here. That's why it is effectively a left shift by 4 bits. But that's really the function of the splitter. And We have used splitter since the very beginning of this class. So it's just a matter of connecting those concepts together to understand how they work, as one unit. All right, so I got distracted. Right. Okay, so now we want to look at the pathways. We know RAM should be active, so we'll take a look at RAM. And sure enough, it is active. It is in read mode because LD is a 1. So now our interest is shifting to who is specifying the A port of RAM. We track it down to the multiplexer. This multiplexer has its select of 1, which means input 1 connects to the output. So now we track down input 1, and input 1 connects to the processor, the PC, the program counter. So this is confirming. Okay, let's see what this is confirming in the opcode table. What I have just mentioned is confirming this part over here. We are using the program counter as a pointer to point to a location in RAM, and we are reading from RAM, and that's why this part is on the right hand side of the assignment, because this is what is supplying the value. So what we want to figure out next is how is the D port connected to the rest of the processor? Who is paying attention? So this is the D port, so we follow all of these things, but we kind of have the answer already, right? Because we know this is going to be used to update the program counter, except you can see this node does not reach the program counter by itself. It got pretty close, but not exactly, right? So it got here, and this is a multiplexer. We can see the select is a 1, so that means input 1, which is the highlighted node, is connected to the output of this multiplexer. So now we track down this node. This node goes into another multiplexer, but we can see how the select is also a 1. So in this case, this also, this node, which is input 1, is also connected to the output, and now we have completed the entire path from the D port of RAM to the D port of the program counter as a register. So for the next rising edge, whatever is on this particular node is going to be used to update the program counter. What is not displayed here is how does PCMux get a value of 1? That part is not entirely clear, because PCMux is actually not one of the actual outputs of the D port of ROM. So we want to track down how PCMux is actually determined. As it turns out, the PCMux is determined up here using this part of the subcircuitry. So this is PCMux, and PCMux turns out to be the output of a particular multiplexer, this particular one. And this multiplexer is kind of funny. It has the first 5 inputs coming from the flags register, and then we have bit 5 and bit 6 connected to a constant of 0, and then we have bit 7 connected to a constant of 1. So this multiplexer is ultimately what determines the value of PCMux. So you have to look at the actual PCMux because it is the select of a multiplexer where the output of that becomes the select of another multiplexer. So this is like 2 levels away from the signal that we are interested in. This one does come from the ROM, and it has a value of 7. So when the select is 7 or 111 in base 2, then we are telling this multiplexer to take the input 7, which is a constant of 1, and make it connected to the output, and that is why the PCMux is a 1. And PCMux being a 1 is what is causing the program counter's D port to eventually connect to the D port of RAM. Alright, so I'm not seeing any questions in the text channel. So if I do a Control T right now, which is a rising edge, we will see the program counter updating itself to, guess what, 05. So there we go. And then we're going to have a falling edge. The falling edge is going to increment the microcode pointer from 400 to 401. 401 is the one that has the most significant bit set, and when you look at the most significant bit of the output of the ROM, which is bit 25, it goes into this OR gate. The output of the OR gate goes into the reset pin of the microcode pointer, which means the microcode pointer will immediately reset to 000, quote unquote, as soon as it gets to location 401. So we won't even see it getting to location 401 because it happens so quickly. But effectively, we're getting back to the fetch cycle. So Control T right now. So you can see how we got back to location 000, which means we are now fetching again. And the location we are fetching from is determined by the program counter, which we can barely see up here, which is 05. So we are now going to location 05, which is where the halt instruction is. And then last week I explained how the halt instruction works. It's basically getting stuck because it keeps decoding itself, so it's not going to go anywhere. So that kind of concludes the analysis of how the Jmpi instruction executes. All right, so we got questions coming in. Very good. Oh, okay. All right. Are there any questions? Okay, I'm gonna pause here a little bit to see if there are any questions coming in. That's interesting. Oh, right. Shall we rename it as the F cycle? I don't want anyone to send an email to my dean and say, Tack is cussing in class. He keeps saying, the F cycle. I'm just kidding. All right. Well, on the other hand, without the F cycle, none of us would be around here, right? So, there was that. All right. Yeah, that's it's a truth that most people don't want to think about or to recognize. Anyhow, so this is the
Real quick,
yeah. Go ahead.
can you go back up to the upper right corner of the processor
Upper
where
right
the
corner.
PC mux are?
Yes. All right. Go ahead.
So the first mux that's closest to the flags, the first 5 bits, they're only responsible for the flag bits, correct?
Well, let's click on it and see how they're connected, right? So let's click on this wire. Oh, okay. It's hard to it's hard to click on it because it is in a big mess of stuff. That's just one of them, and if I can click, oh, there we go. So you can see how the splitter tracks its way all the way back to the flags register, and it's going to the Q port of the flags register, which is always on. You cannot turn off the output of a register, so that's why these 5 bits, they're always corresponding to the 5 bits of this flags register. This flags register, unlike the other registers, only has 5 bits.
Right.
Are we good?
Okay, because I was just making a connection because I was testing out different jump conditions over the weekend, so
Oh, cool. Yeah,
at
so
least
this
trying
is
to.
this is how we perform conditional branches, which I'll explain in today's lecture as well. But right now it is unconditional because the BC MuxMux is specifying a constant input. So this one does not depend on the flags register in any way. This is just always 1. And that's why PC Mux is just a 1 at this point for the Jmpi instruction.
Right, got it.
Okay,
All right, that
excellent.
clears up a bit.
All right, cool. Very good. All right, so we have just explained the Jmpi instruction. It is a unconditional branch instruction, which is equivalent to the goto statement in most programming languages. Okay, we just continue execution at wherever that thing specifies. Now, when you're actually programming, typically the Jmpi instruction would be followed by a label unless you feel comfortable counting locations by yourself and then say, I think where I want to go to is a location, 67. Yeah, I mean that's going to be hard. Okay, when your program gets larger and larger, and you want to say, okay, occasionally I miss a few instructions. I'm gonna insert a few instructions. Guess what? That's going to change the count of all the locations, and then you have to go back and fix everything up. And if you forget one, okay, if you miscount by one, the assembler is not going to complain. Your execution, the execution of the program will simply be way off because of that one location off. So the practical use of the Jmpi instruction is not to specify a integer by yourself, but to specify a label designating where it is supposed to go. All right, Richard is typing in the text channel. And I'm going to switch back to my Joplin screen so I can remind myself what I'm supposed to do next.
I'm just going to unmute myself because I was taking too long to type. I was going to ask, would
Yeah.
you say the labels are synonymous or similar to like the pound defined in C?
No, they're really synonymous to labels in C.
Okay.
they're really synonymous to labels in C because in C, a label, which is also just an identifier followed by a colon, it designates a place for a go to get to. So from that perspective, a label in the assembler so far is really doing the same thing as a label definition in C and C++ and most other programming languages.
Okay, got it.
hmm Yeah, so I can actually replicate that program over here so you guys can see, you know, one way to do this, right? So I can do a JMPI to label L1, and the assembler assembles right away, and it's going to complain, and it says unresolved reference of label L1. It changes everything to lowercase because the assembler is actually case insensitive, so everything is actually in lowercase. So now I put 3 no ops in between, and here is my actual halt instruction. Wait, I have to put a label first. So label L1 is over here, and then the halt instruction is at where the label L1 is defining. So now the program assembles without any problem because column B is used for reporting errors. And then when we look at the assemble tab, we have a pretty good view of what the bytes are supposed to be and where they're supposed to go. And you can see how location 0 has 4 0, and that makes the 0 5 at location 1. And then we have 3 0 zeros, which are corresponding to the no op instructions. And then at location 0 5, we have a 0 1 because of the halt instruction. Yeah, L1 is at 5, so you can actually see how label L1 is defined at location 5. So yeah, so it does work. It works out exactly the way I mentioned that it would. Yes, yeah, we have to count from 0. Yes, counting from 0 is kind of the key to how we figure out where the bytes are supposed to be. Cool. All right, so you have all of these tools available to you. The assembler, the opcode table if you want to do things by hand, Logisim itself, okay, and Logisim, the processor in Logisim is quote-unquote self-documenting because all of the components are fairly basic. We have multiplexers, demultiplexers, they're essentially switches. We have RAM, we have ROM. They're basically tables, they're arrays. Okay, one is read-only, one is a const array. ROM is basically a const array, and then RAM is a typical array where you can change the content or you can read the content. And then we have registers, which are more or less like integer variables. Okay, sort of. Okay, because each one can be changed, and the output is always there. It's always outputting its own value. Let's see. The text channel says, would that be location 4 there then? Not quite sure what the question is asking. Would that be location 4 there? If I get rid of one of the no op, then label L1 would be at location 4. Not sure whether that's the question. Alright, so the next question is, it looks like it's starting at location 0 and then skipping 1 then 2. Nope, well, okay, it didn't skip. Okay, it did not skip because the first instruction, which is JMPI L1, takes up 2 bytes. It takes up 1 byte for the opcode for 0. It takes up another byte for the immediate value of 0 5. So it's taking up 2 bytes. Yeah. Mm-hmm. Yep, there we go. That was actually in one of the first labs that has to do with the processor and the assembler. I was asking you guys about, okay, look at the byte that has a value of blah. Where is it? Or I think it was the other way around. Yeah, I gave you the locations and I asked you what is over there, and then because it doesn't show up on column W, most people got confused by that one. And that question was actually by design to be confusing because I was trying to get you guys to think about how to count locations. How do we use column X and column Y? So that was that. All right, cool. And I think everything is addressed. Okay, very good. All right, so moving on to back to Joplin because I need a reminder of what I'm supposed to talk about. So unconditional branch is JMPI. We talked about this sample program. It's all done. How PC is used in the fetch cycle. Okay, that is important because PC, the program counter, really is just saying, hey, the next instruction is over here. So by changing the program counter, we are changing the flow of the program because normally it just goes for the next instruction. But if we just say, hey, this is the value that we want to stash into the program counter, we are then changing the flow of the program, which is the same thing as what a go-to statement would do in a C program. So now we're going to move into conditional stuff, okay? But before we get to conditional branches, we'll first talk about comparison because, because otherwise, why do we want to pay attention to the flags of the flags register, right? So the flags in the flags register reflects the result typically of a compare instruction, even though a subtract or an add instruction would also change most of all of the flags. Okay, would influence all of the flags in the flags register. So we're going to take a look at the compare instruction and then figure out what a conditional branch is going to do based on the flags. All right, so getting back to the opcode table, compare, which is CMP, is, where is it? It's right here. Okay, so this is the CMP instruction, the compare instruction. It's not CPR. Okay, CPR is copy register, which is a much easier opcode to understand. This is compare. So the compare instruction has an opcode of 1110, which is a E in hexadecimal, and then we specify which register is X, and then we specify which register is Y, 2 bits for each register because we have to select one of 4 registers. It takes 2 bits to select one out of 4. And column C is confusing in this case. Column C says we are subtracting Y, we are calculating X minus Y. But the result, the difference, is not stored anywhere. And if you were to write some code like this in an actual C program, your professor is going to go like, it's not syntactically wrong, but why would you want to do something like this? Because it's useless in a regular C program. But in assembly language programming, it is not useless because this will basically change the flags. It will affect the all of the 5 flags, and now the question is how, right? So we're gonna test this specific instruction and just kind of check out what it's gonna do. To hand assemble something like this, now you can certainly say, we want register A for XX and we want register A for YY, then it becomes just E0, but that would be a super boring compare to do because anything minus itself is going to be a 0. Okay, so it's not a whole lot of fun to do that. So let's try to subtract, let's try to subtract register B from register A. So YY is going to be 0, 1, and then XX is going to be 0, 0. And then we'll have a halt instruction right after that. Alright, so we got a new question in the text channel. Do we need to put something into the registers? Yes, we do, but we're going to do it the lazy way, which is going straight into the register bank and just type over the value of the registers, because we are really just testing, right? We are just experimenting with these instructions. We are not really trying to write a program that has a specific thing to do. So we're So we can take a little bit of a shortcut here just to demonstrate what the instruction is going to do. Alright, so we're back to Logisim, and anytime you want to test something new, it is usually a good idea to go to Simulate and then click on Reset Simulation, which is also Control R, so that everything starts from the beginning again. So we'll go ahead and hand assemble our code, which is E1. Oh, okay, I have to click it first. There we go. So we are hand assembling our code, which is E1, because we have 1110 as the most significant hexadecimal, which is E. And then we have 00 to specify register A, and then 01 to specify register B. So we are subtracting register B from register A, but we are not updating register A after the subtraction. Okay, so we are tossing the difference away, but we just want to see how the flags are influenced. And just typically, we just want to put a halt instruction right after this. We're not going to be getting to the infinite cycle of the halt instruction, but it's just good practice to specify that. And now we go into the register bank because everything is reset to 0, including all the 4 registers. These 4 registers are special. Even though the program counter is a register, the instruction register is a register, the flags register is a register, those other registers are not directly software accessible. These 4 are. So that's why these 4 are kind of special in a way. So what we want to do is to do a comparison where the signed interpretation is going to say something that's different from the unsigned interpretation. And guess what? We'll even do an overflow thing too. Okay, so we are going to specify 80 in A. Okay, so we'll put an 80 here, and then we'll specify a 01 in B. Okay, my watch just buzzed. It's time to take roll. Exciting stuff. Exciting stuff. So today's row taking word is trace. So I'm going to put it in the text channel first, and then I'll just go ahead and unhide the row taking activity. So that would be down here somewhere. Oh, right there. Okay, I'm staring at it. Alright, so if you refresh, you should see the row taking activity. The word is trace, T-R-A-C-E. It is in the text channel. Alright, so in the text channel, Matt says, so the 1 in E1 comes from exactly, yep, exactly. 00 specifies register A, and then 01 specifies register B, but we are not subtracting 01 from 00. We are subtracting the register identified by 01 from the register that is identified by 00. So the 00 minus 01 is not entirely true. So the best way you can specify that is to specify something like this, reg 00 minus reg 01. So in other words, in this notation, I'm looking at the register bank as an array of registers. So we are subtracting the register with quote-unquote index 01 from the register that has an index of 00. It's not exactly that, but it's close to that. Instead of saying, we are dealing with 0, 0 minus 01. It is the other way around. It is the minuend is register A, the subtrahend is B, is register B. So it's not 01 minus 00, it is what I just typed in the text channel. But we'll see that, okay? We are going to verify that in the simulation. Alright, so I think the row taking activity is done for the most part. And now we're going to get back here to look at these 2 specific values. Yeah, not a problem. Alright, so we're gonna take a look. We'll look at the 80 and ask, what is it representing? Well, technically speaking, 80 simply means we have 1, 0, 0, 0, 0, 0, 0, 0. It's just a bit pattern. It has no intrinsic value that is trying to specify. It's just 8 bits. Okay, it's a sequence of 8 bits. Okay, where the ordering is important. So when we want to interpret that bit pattern and say, if I want to look at this as a signed integer, what is it going to be? It's negative 128. Or if you say, if I want to look at this as an unsigned integer, what is that? It's going to be positive 128. And as you can see, A is very extreme, depending the value being represented by the bit pattern is very extreme. If you see it as a signed value, it is as negative as it can go. If you look at it as an unsigned value, not quite as positive as it can go, but it is pretty up there. Okay, it's halfway up there. Register B is 0, 1, so no matter how you look at it, 0, 1 is just representing 1. Okay, so we are subtracting 0, 1, just 1, from either negative 128 or positive 128. But we are not going to store the difference. Okay, we just want to see how the flags are going to be affected. So in this case, let's do something by hand first, because instead of relying on the circuitry to tell us exactly what the outcome is going to be, let's do it by hand. Okay, so we are gonna let me see what we so I need a bunch of spaces to start the 1, 2, 3, 4, 5, 6, 7, 8 to start the what is the word? It will basically give us the illusion of a table. No, do I need more spaces? I think it needs 5 spaces to do that. Oh, that's just a tab character, which is not what I want. Okay, let's 1, 2, 3, 4, and then we should do the same thing over here. Oh, right, I think I need an empty line here first. There we go. Okay, so that's sort of what I want, but I need to line up the spacing a little bit more. Oh, that is ugly. Alright. Well, that means I'm just gonna have to do this interactively because I can't really see it. Alright, so the result is actually going to be a 0 followed by all ones. 1, 2, 3, and then 1, 2, 3, 4. And then the overall borrow is going to be a 1. Okay, 0, sorry. So the overall borrow is going to be 0, and that would be the same thing as what we usually refer to as T bracket 8 in this case. So this is relating all the way back to the terminology that we used when we talked about binary subtraction. And we also want to look at the other flags, right? So the other flags that we are interested in would be the Sine Flag. So the Sine Flag is a 0 in this case because the difference starts with a 0. The most significant bit of the difference is 0. And that is usually called D7 because it is bit 7 of the difference. Overflow. Okay, so let's check out the overflow. Overflow is a 1 because we have 1, 0, 0. Okay, because we have 1, 0, 0 here. So overflow is going to be a 1. And then the L flag, which is the exclusive OR between the sine and the overflow flag, is going to be a 1. And then this time we have one extra flag, which is the Z flag. The Z flag has been explained already. It is the result of the NOR of all the bits of the output of the operation. So even though the output is not stored anywhere, it is still affecting the flags. So we can quite clearly see that not every single one is a 0. So that means the Z flag is going to be a 0 because it is the NOR, the negated OR, of all the individual bits of the output. Alright, so now we have a theory of how the flags should be. Let's go ahead and check out the actual execution of this code here. So we are going to go back to Logisim. We have these 2 specific values, and then we go back to the processor, and we're going to fast track through the first four edges, because we know we have the fetch, then we have the decode, and then we get to that location. So I'm just gonna quickly type four control T's. So we got 1, 2, 3, 4. There we go. Okay, so now we're getting to E10, which as you can see, it is just the same as the opcode, but with one extra zero to the right hand side, for the four binary zeros, because of how the merger works. But the interesting part is, okay, so what, right? Well, in this case, let's check out what is active and what is not active. RAM is not active in this case, okay, because you can see RAM is not active. What is active is the ALU, because the ALU has its own enable pin. This is the enable pin for the ALU itself. So whenever the ALU is active, we want to check out what is it going to do. So we go into the ALU first, because that's easier to see what it is going to do. Op cell is operation select. It is 001. So it is being used to hook up to a whole bunch of components. The 2D multiplexers as well as the multiplexer, they are all selected by op cell. So op cell says, okay, the second output is what we want to deal with. So it's going to a subtractor. And this multiplexer has exactly the same select pin, except the inputs are different. So we'll deal with that later. So we are basically activating the subtractor in this case. The multiplexer here is the quote-unquote concentrator, or the selector of, okay, so whose output should I use here as the actual output, because we have 6 mechanisms that can compute something. In this case, because the select pin, which is this one, is also connected to the op cell input pin here, it is also just selecting input 1 to connect to the output pin. So collectively, these two demultiplexers and this particular multiplexer, they work together to basically say, which of these following computation am I doing for this particular round? That's all they're trying to do. And this time we're doing a subtraction. That's how we are, performing the operation. So out of the subtraction, we have a B flag coming out. Okay, this is borrow out, and borrow out with a 8-bit subtractor is technically the same thing as our T8. Okay, that's why I used T8 earlier to denote that particular flag. But this is a tunnel. Tunnel cannot get out of a circuit. Only input and output pins can get out of a circuit. So just seeing that this is a tunnel means, okay, now we need to track down where the tunnel is going. So we have to find other references to B, and here's one. So B and C are both going through a multiplexer, and the select is also connected to the op cell input pin. So in this case, we are selecting input 1, which is our borrow flag, to become C out. Okay, and C out is actually being merged into the actual flags out output pin. So flags out as an output pin, the bit 0 of flags out is actually just the borrow flag in this case. So that explains one of the bits. Okay, bit 0 of the flags register is the borrow flag, which is also known as the carry flag. I know it is confusing, but most computer architectures would basically look at carry and borrow as quote-unquote the same thing. Alright, what about the other flags? What about the sine flag? The sine flag is easy. Okay, the sine flag is right here. We just tap the output of this multiplexer here, and whatever is bit 7, you can barely see the 7 here. Okay, there's a little 7 here. So we just take bit 7 of whatever the output of the operation is, and we call it S out. S out is one of the things contributing to flags out, and this is S out right here. It is bit 2 of flags out. So that means bit 2 of the flags register is going to store the sine flag of whatever of the result of the previous operation. Let's check out the Z flag too, because that's also an easy one before we get to the more difficult ones. So the Z flag is right here. It is the result of the NOR, negated OR, of all of the bits coming out of the multiplexer. So since we have 0 followed by all 1s here, not all of them are zeros, which means at least one is a 1. So if you have a regular OR gate, if at least one input is a 1, then the output is going to be 1. But since this is a NOR gate, that one is negated to become a 0. So Z out is a 0, and Z out is bit 1 of the merger that will go out to become the flags out pin. So now we're going to get to the more complex one. What about the overflow? So overflow here is a tunnel by itself, and it is exclusive ORed with S out, which is the Sine flag. So this kind of explains, this is consistent with the L flag being the exclusive OR between the Sine and the overflow flag. That part is pretty easy. What about the overflow flag itself? How is that computed? So over flag is the output of this multiplexer, and we see this multiplexer is also using OP cell as the select pin. But when you look at the input, the two inputs, for operation 0, it's using this wire. For operation 1, it's using this wire. Operation 0 is add. Operation 2, Operation 0 is add. Operation 1 is subtract. So when you look at this bunch of gates, it is actually doing what we have already seen as the overflow flag binary expression. It is negating the Sine flag of the minuend, and then ending it with the non-negated Sine flag of the subtrahend, and also ending it with the non-negated Sine flag of the difference, which is the last one here. It's S out, and then the other conjunction is represented by the other AND gate. So this is how we do the whole thing in hardware, okay, which is basically the same thing as what we have seen already as the equation or the formula to calculate the overflow flag after a subtraction. Do we have any questions now? And is everybody making a connection between what we are seeing here with what we have learned in binary subtraction? Oh, sure. S1 and S2, they are really just the Sine flags of the two inputs. So they are pretty easy to figure out. There we go. This is where we tap bit 7 to become S1, and this is how we tap the input into S2. So that means S1, for as far as the subtraction is concerned, is the Sine flag of the minuend, and then S2 is the Sine flag of the subtrahend. Are we good so far inside the ALU? Cool, cool. All right, so now we're going to zoom out again because we want to know, what is going into in1 and what is going into in2 of the ALU. So now we have to track this down and say, oh, it's the output of a demultiplexer. So we better make sure that the select of this demultiplexer is 0, 1, because the output 1 is connected to the input, the only input here. So when we click on the select, we say, okay, that's good. Okay, 0, 1 is indeed the select of this demultiplexer, and it is enabled. Very good. So it is coming out of out 0 of the register bank. So now we go into the register bank and say who is, which register is having its content connected to register output 0 of the entire register bank. So now we click here, and then we track down this wire, and this multiplexer has 0, 0 in it, which means input 0 is being used to connect to the output of this demultiplexer, and we have indeed having register A connected to the output 0 of the entire register bank. And then we have a question of, do the Sine flags not matter or not change for the other operations in the ALU, like the not operation? You are correct. That's why we have the multiplexers. So other than the add and the subtract operation, the overflow is just going to be kept. Whatever is the overflow flag in the flags register is maintained for any operation other than add, subtract, and compare. So Terrence is correct. The flags overflow, and the L flag are maintained for anything other than add, subtract, and compare. Very good. Good observation. Good question. All right. So I'm just gonna, also go back out and say, what about input two to the ALU? So input two is this one. It's coming from a multiplexer. The select pin of the multiplexer is a little bit hard to see because it is actually this node here. That is, that's the select pin. It is 0. So we are looking at input 0 of this multiplexer, and that is coming out of a demultiplexer here. I know this looks really convoluted because I had to add a few components, to support the increment and the decrement instructions, and that's, it's basically a fix on top of the original architecture prior to the implementation of increment and decrement. That's why it looks kind of messy. Anyway, this is a demultiplexer, and we better make sure output 1 is the one being selected, and that is true because the gray dot is marking the select pin of a demultiplexer and also a multiplexer. And now we look at the input here. It's coming out of the out one of the register bank. Then we look into the register bank and ask who is outputting to the register bank's own output 1. This is register bank output 1. This is how we do the select for this multiplexer. It is 0, 1, and 0, 1 is going to select input 1, which is connected to the output of register B. So now we have completed the analysis to say, okay, now we are convinced that register A is going into the minuend input of the subtractor, and then register B is going to the subtrahend input of the subtractor inside the ALU. Whew. Man, that's a little journey, right? That is kind of what I want you guys to do on your own at least a few times. So now we're going to go back to the ALU and find out, okay, what is the output of the ALU? Okay, so we'll go back into the ALU. Yes, the test is going to involve, having, it will check to make sure that you guys understand what I just said. So, so the answer is, I guess, you can call it yes. All right, so we are interested in the output. The output is quickly ignored. It's not being stored anywhere, but it is 0, 1, 1, 1, 1, 1, 1, 1, or 7F in hexadecimal. So we got that checked out. And then the Z flag is a 0. We got that. Overflow is a 1. We got that. The carry flag or the borrow flag is a 0. We got that. And also the L flag is a 1, which is the output of this exclusive OR, and we got that. So at this point, if I go back to the outside and we look at the flags register, which is where? Up here. Okay, so if we look at the flags register, we're going to have a rising edge. So the rising edge is going to store the bits that we have just figured out. That's not going to work because the question is not going to be strictly, just explaining, how the processor works. So yes, I have spent years to try to figure out how to ask the question so that I can actually see whether people understand the concepts or not. Right. Okay. So getting back here. All right, so these 5 bits, okay, they are arranged in this particular way. The most significant bit is the L flag. Okay, I can only remember how to do it in a backward way, so it's C, Z, S, O, L. There we go. So these are the 5 flags arranged with the most significant bit on the left-hand side. So in this case, we should end up with a bit pattern of 1 because that's the L flag. Followed by the overflow, which is a 1, followed by the Sine Flag, which is a 0, followed by the Z flag, which is a 0, and followed by the C, basically it's the borrow flag, is also a 0. So these 5 bits should be stored in the flags register when we are done. In hexadecimal, these 5 bits can be read as 1, 8. Okay, this 1 here is the 1, and then these 4 bits here is the 8. Alright, so knowing that, we are now going to have a rising edge so that we can check out what's going to happen to the flags register. So Control T right here, it is indeed 1/8, okay? And you can also see how that immediately changes the state of the least significant 5 bits of this multiplexer, because they are basically just looking at the 5 bits of the flags register. All right. Okay. So that is how the compare instruction works. Okay, that's it. Okay, all it does is to change the flag register. The difference is not stored anywhere. It's not the subtract instruction. The subtract instruction does take the output of the ALU and then loop it back to the register bank and store that to the first register. In this case, it would have been stored into register A. All right. So the next question is, okay, let me take a look at the time. We got 20 minutes. I think that's sufficient time. So the next question is, how do we utilize the flags register? Okay, I mean, the flags register is hidden all the way up here, and it would appear that the only thing it does change, okay, the only thing that makes use of the flags register is this multiplexer here, right? And this multiplexer is, we can only use PC mux coming out of the ROM to tell this multiplexer which input we want to use to connect to its output, which in return is PC mux. Okay, so at this point, I'm going to do something that no one else should do, which is changing the program on the fly and just say, let's give us a conditional branch instruction right after the compare. So instead of the halt instruction that we have already specified here, let's do a conditional branch instruction. So now we go back to the opcode table, okay, and go to one of the conditional branch instructions. We don't need to look at every single one. We can just look at one, and the one that we want. So these are the conditional branch instructions: JLI, JOI, JSI, JCI, and JZI. These are the conditional branch instructions. And when you look at column C, I hope by now you are comfortable with ternary expressions because I use it a lot. So each one is looking at a specific flag, L, O, S, C, Z, to determine whether the program counter should be updated by whatever it points to or whether it should just increment. This is how decisions are made at the lowest possible level inside at least this particular processor. All right, so this is actually a monumental moment of this class. Monumental moment. Wow. Okay, it's kind of like a Kung Fu Panda saying, I'm the legendary legend. But this is it. Okay, this is very, very important, because all the fancy logic, all the fancy control structures that you have in C, C++, and all the other programming languages, every single time when you can say, I can proceed this way or the other way, boils down to this. Okay, it boils down to whether the program counter should be updated by what it is pointing to, or whether it should just, increment. That's it. Okay. But what we're interested here is to say, what is the opcode? Okay, let's pick, what did I say? JLI. So JLI has an opcode of 41, and then we also want to specify where to go to. So let's go back there and do some additional coding here. So we want to specify a 41 here, and if it does want to branch, okay, if the L flag is indeed a 1, right, so if the L flag is indeed a 1, we wanted to get to location, let's go ahead and use location 05 again, and we'll put a halt instruction here. And if it is not, we want to proceed, and we'll put another halt instruction over here. So either way, the program is going to stop executing after the conditional branch, because it's either proceeding to the halt instruction that is right after the conditional branch instruction when the L flag, if and only if the L flag is a 0, or if the L flag is 1, then it's going to proceed to whatever the immediate value is telling it to go to. In this case, it will be location 05, and it is also going to hit another halt instruction over there. Alright, so now we can continue the execution of this program, because I just hacked the program, halfway through tracing, a simpler program. Alright, so now we are going to do something that is not very exciting because it is a falling edge. The falling edge is going to make the microcode pointer to go to location E11, which is basically just 2 followed by all zeros, which means the most significant bit is a 1, and it is going to be used, oh, not this one over here. So it's going to be used to, it's going into the OR gate. The output of the OR gate is going to reset the microcode pointer. So here goes, okay, Control T, and the microcode pointer gets back to 0. So now we are fetching again. Not very excitingly, we are now fetching from location 0, 1, because the program counter was auto incremented, as the as we have a rising edge when the microcode pointer is at location 001. So that part has been explained in the lectures from last week already. So now we're going to do another Control T 4 times so that we can get to the conditional branch instruction. So here we go. 1, 2, 3, 4. Alright, so now we are at location 410 in the ROM, and the output here is the key to determine how is a conditional branch instruction done, at least in this case, the tax toy processor. All right, so now we are going to look at PC Mux Mux. PC Mux Mux is no longer the boring 7. Okay, 7 is boring because 7 means the multiplexer is connecting its input 7 to its output. Input 7 is just a constant of 1. So every time PC Mux Mux is a 7, all we are going to say is to say, hey, PC Mux is just going to be a 1. That is boring. But now it's a little bit more interesting because PC Mux Mux has a value of 100 or 4. So we are connecting input 4 of the multiplexer to its output. And this turns out to be bit 4 of the flags register, which you probably recall from the previous step. This is also the L flag, representing the signed comparison of 80 versus 01. 80 is a smaller value. It is less than. That's why the name L. How is the program count PC Mux going to be used in this case? PC Mux is utilized here as well as utilized here. So we know the program counter is going to be updated because PCEN, which is the enable of the program counter, is a 1. So what we don't know, or what we need to figure out, is how it's going to be updated. And because PC Mux is a 1, it is selecting input 1 to connect to its output. This in return is going to this Mux here, which also has its select being a 1, which is coming from this wire. This particular wire, or this node, is coming out of RAM. Okay, it's coming out of the D port of RAM. RAM is selected in this case, and every time RAM is selected, you want to ask who is specifying the location of RAM. So we track down the A port. A port is coming out of this multiplexer. The multiplexer has a select of 1, so we track down input 1 of the multiplexer, and it goes all the way back to the program counter. This is why we have this notation here. L is a 1 in this case, and that's why we are using whatever the program counter is pointing to in RAM to update the program counter itself. Effectively, it is a Jmpi instruction, the way it is wired at this point. Now, when I say the way it's wired, I'm only talking about how the RAM component is connected to the program counter. For that part, it is the same as a Jmpi instruction. But why it is connected that way, that has to do with PC Mux Mux and the multiplexer that takes the output of the flags register to change or to affect what PC Mux is going to do. So that means if I go back here and have another Control T, another rising edge, then it would have updated the program counter to 05, because if you just click on this wire, it is already 05. So we kind of know, if I just do another Control T, PC becomes 05, which means that's where we're going to get the next instruction, which is basically the same thing as, oh, we are just continuing execution at location 05. What if the L flag is a 0? Right? I mean, what if it is a 0? According to the documentation in the opcode table, it will simply increment. How do we see that that is the case? Well, that's actually not difficult. We don't have to unroll the experiment all the way back to the beginning and change the register A and B in order to make the L flag a 0, because I can do the next best thing, which is going straight to the flags register, highlight it, and then I just type 0, 8 here. And you can see how the content of those flags register is changed right away. Yes, I cheated because I just injected a different value into the register right before the rising edge to update the program counter. But I just want to see, how the pathway is changed when a flag is a 0 instead of a 1. So what has not changed are all the control signals coming out of the ROM. The PC mux is still a 100 in base 2, which is a 4. So we're still connecting input 4 of this multiplexer to its output, except this time bit 4 of the flags register is a 0 and not a 1. And that's why PC mux is now a 0. So when we get to the program counter, okay, which still has PCEN being a 1 because PCEN is coming out of the ROM, but the way it is connected is different now because this multiplexer now has a select of 0. So we are now tracking down input 0 of this multiplexer, and you can see how it just kind of loops back to the incrementer here. And this incrementer is taking the OR out of this thing here, and the address mux itself being a 1 is going through the OR gate, and that is why we are incrementing. Okay, we got a... Oh, okay. I thought I saw a post. Maybe it's just on a different channel in Discord. So anyway, this is why we are now incrementing the program counter, because when you click on the wire or when you click on the node going into the D port of the program counter, it is just 03. We're just incrementing and go like, oh, let's go for the next instruction. So this is in many ways, a very, very important discussion, because this is how decisions are made when you get all the way down to the level of assembly language. Okay, this is how decisions are made. We are just looking at some flags. Okay, most processors have these 5 flags, and we just look at each flag and go like, okay, well, okay, I shouldn't say each flag. We look at one of the flags and we ask, what is the value of this flag? If it is a 0, I continue execution. I just go to the next available instruction sequentially. Or if it is a 1, then I'm going to use whatever content that the program counter itself is pointing to, and then use it to update the program counter itself, effectively doing the same thing as a Jmpi instruction, the unconditional branch instruction. Alright, so I'm going to pause a little bit, see if you guys have any questions in the text channel, while I go back to Joplin to remind myself what is the next thing that I need to talk about. I see it. I see it already. So I'm just asking about any text questions. Nope, no questions from the text channel. Oh, here comes one. I'm good. Okay, all right. Now, I know this is a lot of material. Okay, I know it sounds kind of, I wouldn't say complex. Okay, it is tedious. Okay, there's a big difference between tedious and complex. Complex means conceptually there are things that are difficult to wrap around. That would be complex. Tedious simply means, oh, there's a lot of details to track down, and then and then we have to connect all of those low-level detail stuff to kind of understand the bigger picture. That is tedious. Okay, and what I have just described is tedious, not really so much complex. In other words, it's really a matter of going through the exercise of what I just did, tracking things down, okay? Because all of those nodes, all of those wires flying around in the text-toy processor in Logisim, that's going to help you analyze, okay? Click on one and ask, oh, where is it coming from, or where is it going? Okay, look at all the select pins of the multiplexers and the demultiplexer, then you know how things are connected. And then you look at the registers and ask, is this register enabled? If it's not going to update itself. Oh, this one is enabled, so that means the next rising edge, that register will update. Then I have to ask the question, how is it going to update? What is the new value? Who's specifying the new value? it's all about tracking things down like that, okay? And everything starts with the ROM, because the output of the ROM is what configures the rest of the processor and determine what the processor as a whole is supposed to do. So that would be the how you want to kind of practice doing this, is to practice analyzing how instructions execute. At least replicate the ones that I have done so far. And if not, if you want to do a little bit more, you can certainly go to some other instruction and go like, I want to figure out how that one is getting the job done. Alright, so now we are moving on to how to trace the execution of code, which is what you need to do for today's lab. Yes, there's a lab today, and you have to track down the execution of code. So there are some ways that are easy to set up, but it's harder to interpret later on. And then there are ways where it is difficult to do, but it's easy to interpret the result. And then there's the way where it is easy both ways. Obviously, some people would go for, I want to see how that is. Okay, well, I'm going to let the class vote a little bit here. Which one do you want me to talk about first? For at least just the lab. The first one is everybody can do it. You don't need Linux, and it's pretty easy to do, just difficult to read. There's no easy. There's no that is live. Easy both ways doesn't exist. The tedious way. Yeah, I think we should go for this way first, okay? I changed my mind. The second way is probably the most appropriate way. I'll describe it first, and then we'll go back to the first one. So the painful way, which is multi-step, is not quite as bad as you think it is. Okay, it is just a matter of there's a little. You just have to write down the instructions. Okay, step-by-step instructions. First we do this, then we do this, then we do this, then we do this. It's not really that bad. So I'm gonna go for that approach first. So to go for that approach, I'm going to give you a different program. So we'll go to source, get rid of this one, and then I'll give you a different one. So this one, to use this approach, you have to start with a no op as the very first instruction. The lab already has no op as the first instruction for the one where you have to trace down the execution of the program. So that's done already. No need to worry about this part. And I'm going to load LDIA with a value of 5. I'm setting up a branch that will go through like 5 times. Then we have a label L1, and I'm going to do AND AA, JZI to L2, decrement A, Jmpi to L1, and then we have L2 specified here, and that's the end of the entire program. Unknown mnemonic. Oh, I forgot about the colon. There we go. All right. So no need to worry about what AND AA is going to do. No need to worry about what is decrement A. This is just a program. Okay. But let's just say that I want to track down how many times the decrement A instruction executes in this case. Okay, so I just want to count. I don't even care about the logic of the program, of why it is executed this many times. I just want to count the number of times that decrement A is going to execute before we get to the halt instruction. Does everybody understand what I'm about to do? What is my focus here? All right, very good. So I'm just to make sure that we remember that. Okay, count the number of times this opcode executes. Okay, so that's what we want to do. You can see the program assembles just fine. No error messages. We go to the RAM file. So this is the step. These are the steps. You might want to jot down the time. It is 10:19 right now. So this way you can go back to the recording and quickly locate which part you need to review to find out what the steps are in order to get your assignment done, to get your lab done. So now we go to file, and then we go to download, and we go to CSV. TSV is going to work too, but I'm going to specify CSV specifically in this case. And in my browser I set it up so that I can determine the name and what to do with the file. So I'm going to save the file. Don't open the CSV file. It's not going to do you any good opening it. So just save it. So I'm going to save it, and I'm going to change the name, because I don't want any space in the name itself, because that's going to interfere with how Logisim works. I think Logisim doesn't like file names with a space in it. I could be wrong. So I'm going to change it to just test. Okay, you can name it any way you want as long as it doesn't have funny characters and space. So now it is saved. The program is saved. The object code is on my computer. I can now go to Logisim. It's very important to go to simulate and reset the entire thing first, because we don't want any leftover stuff from the previous program. We go to the RAM component, right click on it, go to load image, and then we specify the file that I have just talked about. So that would be in my temp folder. All right, and the name is what was it? Test. Yep. So we're looking for test.csv, which is this one, and then specify open. And you can see how the content of RAM is now updated, which means it's time to run the program. You can just let it run at full speed. There's no need to Control T through it. Yeah, this is non-Linux. This is definitely something that you can do in just about any operating system. So now we go to simulate, and we want to take and enable the tick, which is Control K. And you also want to make sure the tick frequency is high, so you don't have to wait too long. So we just enable the whole thing until the halt pin is a 1. So now we can stop. You know what? I forgot. Oh, I forgot. This is not going to save us the file that we need. All right, so I'll still do this, not this way, okay? Because the GUI version of Logisim is not going to be useful in this case. You have to use the command line way of using Logisim, which we talked about a long time ago to capture the output of Logisim. Remember, when we had the earlier assignments where, I think that was the NAND gate stuff, right? Using NAND gate to implement the NOT gate and one of the, I cannot remember, it's either the OR or the AND gate. Remember that one? I gave you a tester, and I show you the instruction to run it using the command line so you can capture the output. That's what we need to do here. So to give you the full output, the full command line, it is java-jar, and then you have to specify the file to the jar file itself. So in my case, it is over here, logisim310.jar. And then you specify the processor circuit file, which is, what you saw in the previous line. So you can do all of this in Windows too. You just have to kind of change the way you specify a path to how Windows like to have paths specified. Changing all the slashes to backslash, and then tilde doesn't work in Windows, so you will have to change to utilize whatever way Windows uses to specify the quote-unquote home folder. And then the rest is something that we have already talked about in, I would say that's week 3 or 4, which is to specify TTY table. We don't need sub this time, okay? So we are not substituting one of the components with yours, so it actually makes it a little bit simpler this way. But we have to specify dash load. This is new because we have a RAM component, and what dash load is doing is it's going to take whatever file we specify here, which is /temp/test.csv, and it's going to load the content of that CSV file into the only RAM component of the processor. Okay. And if you just press the enter key, it should run, and it give you like a whole lot of zeros and ones as the output. I would recommend doing this without the redirection first, just to make sure that it does work. So it's going to give you something like this, and then you look at this and go like, I'm not going to go through this manually and figure out what that means. I wouldn't too. Okay, if I were you, I would not do that too. So that's why we're going to capture the output to a different file. Okay, do not use the same file. So if I'm using CSV as the file of the opcode, and the output is TSV in this case, and you should use the greater than symbol here. This also works in Windows, by the way. The greater than symbol is called redirection. It takes the output of a program and it captures the output of the program into a text file, which in this case is test.tsv. When you press the enter key, it won't give you any output because all the output are now captured in test.tsv. And then what we do is we go back to the assembler sheet or the assembler spreadsheet. In the assembler spreadsheet, there is a sheet called trace raw data. So get to trace raw data and then go to file and then click on import. Now this one you might want to take a screenshot first because you're gonna have to, not this part, okay, by the time we specify the options you need to take you might want to take a screenshot. So we click on upload and then we specify the TSV file that we just captured as the file to upload. So TSV is right here, test.tsv. This is the file that I just captured earlier, and then click open. And what this is going to do is it's first uploading the TSV file, and then it gives you a lot of options of what to do with that TSV file, tab separated value file. This is where you want to pay some attention because we do not want to create a new spreadsheet. We want to replace current sheet. Okay, so this is the first thing. The second one is the separator type. Don't rely on Google Sheet to detect automatically. Say it is exactly tab. And this is also very important, is to uncheck convert text to numbers, dates, and formulas. So this is one place where you want to take a screenshot, or if you don't have time or don't want to do it now, just take a take down the timestamp, which is 10:26:37, and then we click import data. And you look at this and go like, I don't see anything changed. I mean, this is still a whole bunch of zeros and ones and gibberish. Well, move on. Okay, there's a little slider here to slide to a summary tab. And nope, I take it back. It's not a summary tab. It's actually in an earlier part. Analysis. There we go. So go to the analysis tab, which is right next to the assemble tab. And this is a very quick summary of column A is giving you the address of each opcode that executes. Okay, so every single time a particular opcode executes, column A records the address of the opcode. And the rest is actually not important for this lab, so I'm not even going to talk about it. Okay, so now the question is, how do I know the address of the opcode that I need to count, right? So we go back to the assemble tab, and well, actually we have to go to the source tab first to find out which one. It is the decrement A instruction on row 6. Okay, so the row number is maintained between the source tab and the assemble tab, so we're interested in row 6. And you go to the assemble tab, you go to row 6, which is the decrement instruction, because by the time you get to the assemble tab, the comments are gone, so you cannot rely on the comments to remind you which one we want to count, but the row number doesn't change, so you have to use the row number to remind yourself which instruction we're interested in. Column W is the hexadecimal representation of the address. In this case, it is 06. So we want to count the number of times the opcode at location 06 executes. So it's just a matter of counting now. So now you go back to analysis and you just focus on column A and you ask, okay, so how many times did 06 occur here? You can go through it manually and say, okay, here's 1, second, third, fourth time, and here's the 5th time, and then the program terminates. So at location 09, the program terminates. Now, how do you know that the program has terminated at this point? Because there are no more steps performed after this. Okay, so this is the longer way to do this, but it works, okay? Because what we're trying to do is to keep track of when we are fetching, what is the address, what is the program counter. Um, but using this method does require that you have to be able to run the simulator on the command line using this particular thing. All right, so let me see if there are any questions. Okay. All right, so are there any questions about doing it this particular way? Alrighty. So we are basically reaching all the way back, to the past few weeks of this class, other than how to input that in Windows. Okay, well, it's about the same thing. In Windows, it's just that the way you specify the path to specific files is going to be different. I believe I have located links from before of how to specify paths in Windows, and that's kind of what you need to do is to figure that part out. Oh, okay, I just clicked my screen to somewhere else. Okay, we counted how many times 06. What is that supposed to mean? It's totally meaningless. Okay, I just gave myself a meaningless assignment of counting how many times the instruction at location 06 executed. That was meaningless. However, your lab has something that is like that. Not exactly the same, but like that. So I just illustrated the steps that you need to follow to get that question answered. And you kind of have to do it 5 times too, because you have to change the instruction and do it all over again. Alright, so the Linux way is just making a script to automate some of that. Oh, no. Not some of that. Try all of it, okay? So since, Terrence asked that question, now for the rest of the class, if you're not curious, you can go ahead, and I'll give you some extra time to do this too, because the lecture lasted a little bit longer. But if you are interested in the Linux way, this is how I do it, okay? So I'm going to just take the code of the program in the source tab. So take the source tab here and do a select Control C to copy this, and then switch back to my command line. And to do this, I have to switch to my Documents CISP310 folder, which I have a folder called River Spider. Okay, and then I will cat to the source code, and I'll just call this test.ttpasm. The extension doesn't need to be like this, but I just use that Control V is paste. And now I have the program captured in a file called test.ttpasm. It's not necessary. The extension is totally optional. So, what is the Linux way to do it? I just type /submit.sh, press the Enter key, and it's going to do all that work for me. It's going to submit the source code to the assembler, let the assembler finish the assembling, download the object code, and then run the simulator, capture the trace, and then re-upload the trace to the raw output, and then finish the rest of the process. It's supposed to do that. It looks like it's kind of hung up at this point. Not quite sure exactly why it's having a problem, but that's kind of the idea of the Linux way, is having everything pre-scripted. You can actually use that approach, if you use WSL2. I believe, SIGWin may work too. If you just want to use this script, SIGWin, which is what is how do I CYGWIN is something you can install in Windows, so you can actually run bash scripts without having to install Linux itself. So that's one thing that you can do. Alright, well, looks like my script is broken. One of the links is not working, so it's taking forever to do this. So it's not useful to me. I kind of have to fix it first before it will work again. Um, Other than that, we are done for the lecture. Now, for those of you who absolutely cannot get the command line stuff to work, there's an alternative. So you might want to stay a little bit longer on this channel, so that I can describe how you can do that. So let me Control C this first, and we have to restart the version that includes that. We're gonna do it interactively this time. All right, so we're gonna do it interactively this time. It's not working right now. I have to diagnose why it's not working. The district has changed a few things, and it could be the signing in part that is not working. It could be many reasons, but it's not working yet. Um, but the other way works. Okay, the other way, the command line method, that one does work. It's a few more steps. All right, so here I'm gonna load the RAM file. All right. So this one is going to be more painful. Okay, it's going to be more painful because what you need to do is to go to simulate. Okay, and then you go to logging. Okay, use the internal logging ability of Logisim to do it for you. And I need to move the dialog box down so that you can see what I'm going to do here. All right, so you need to figure out what you need to log, and the program counter is one of the things that we have to log. You can pick either one because one is the register output, the other one is the pin that connects to the register output, so they are basically the same. So PC is one that you need to log, and then OP fetch is the other one. OP fetch. Okay, let me go back to the design first. OP fetch is the one pin that indicates whether you're in a fetch cycle or not. It's this pin over here. And when you look at OP fetch, it is the conjunction of the clock, which means you need the clock to be a 1, but you also need instruction register to be a 1. So when both are 1s, that represents that we're in a fetch cycle. So so OP fetch is also one thing that you need to log. So let me go back to the window that indicates what we are logging. All right, so another thing you need to change is when you log the program counter, by default it will log it in base 2. So you're gonna have to change the radix to base 16 because that will make it easier for you to match. Okay, and then you go to File. So you go to File. Every time you select a specific file as your log file, it will erase the previous one. Okay, and you need to do that because you have to do this 5 times. So don't forget to re-specify the log file, because if you don't, then all the logs will be lumped into one single file, and then your count will be way off. So in the file name, I'm going to specify test.log. This is just a text file, by the way. And then you click Save, and then we can now close the window.
One more time.
Yes.
Sorry. Op fetch is a conjunction of clock and what?
Well, everything is still being recorded, which means you can kind of go back to the video to find out.
Sorry, I just wanted to be able to write it in my notes.
Yeah, PC and OP fetch. PC should be logged in base 16, and then OP fetch base 2 is fine.
Okay, I was just wondering for the explanation of OP fetch that it's a conjunction of clock and what if both are
It's a conjunction of clock and the enable of the instruction register.
Okay, cool. Thank you.
Sure. All right, so now we can run the program. There we go. So we'll go ahead and run the program now. We go to Simulate, and then we click on Text Enabled. And it's not going to take much time for it to finish. Then you type Control K again to stop the simulation. And then at this point, we can go check out the text file that we just captured. So let me switch to the command line. In Windows, you don't need to use a command line. You can just use the file manager to navigate to whatever folder that contains your log file. So now I'm gonna use NVim. You can use whatever editor you want to use. Notepad is gonna work in this case. So I'm gonna look at test.log. I think that's the name of the file. So it's gonna look like this. And you don't want to count every single time. Okay, remember location 6 is the one that we want. But in this case, location 6, if you just count the number of times 06 appears, it will give you the wrong count, because we only want to count when 06 is the location and OP_fetch is a 1. So you only want to count when the location matches and OP_fetch is also a 1, and count the number of times that occurs. So this is once. This is the second time. Now, when you're counting like this is the third time, this is the fourth time, and this is the fifth time. And then after that, we can see that it is going to be stuck at location 09, even though the address that says it could get to 0A, it is really stuck at the halt instruction at that point. So we still get to the same count. It's just that this time, we did not utilize running Logisim from the command line, because I think some people may find that a little bit challenging to specify the paths, to various files. For those people who don't want to use the command line option to run Logisim and then use the trace analyzer, this is an alternative to get it done for the lab. But in the future, when we start to actually write programs, this method is not going to be very helpful when we are debugging programs. So eventually we all kind of have to learn how to use the command line way of tracing a program. It's just that at this point, for this lab, this other method also works. Now, I'm almost done, but not quite done yet. Because once you change the program, the lab requires you to change the program. So when you change the program, you're going to have to reload things into the RAM and then run the program again. So when you do that, if you don't want your previous log to clobber your new log, then what you need to do is to go to Simulate, and then go to Logging again, and then go to File again, and then go to Select again. You can select exactly the same file, okay? But when you do this, it will reset the content, because it will ask you, file already exists, do you want to overwrite? The answer is yes, you want to overwrite, because you don't want the new log to be appended to the current log. So between the instructions of that question, which is the last one, you have to remember to do this part to reset the log file. After you do the count, change the program, reload it into RAM, run it again, go through the file, but you have to remember to re-specify the log file so that you basically overwrite the previous log file, and instead of appending to the previous log file. Phew, okay. Oh, the access code for the lab is JXI. There we go. So I think we are done with the instructions. So you can do it either way. Okay, you can do it using the trace analyzer, and probably just look up how to specify the path to specific files in Windows. Or you can do it in this particular way, but it's only suitable for this particular lab. In the future labs, you probably still want to be able to use the trace analyzer. Alright, so I'm finally done with all the lecture stuff, and I used up 25 additional minutes. I'll give you 25 additional minutes for the lab. So it's gonna end at 1:45. Alright, so I'm gonna stop my live stream and screen share, and then I'll pay attention to the text channel for questions.